Hello learner, I am Dr. Ashish Bhargava, Assistant Professor in the Department of Physics of Government Engineering College, Bharatpur. In this lecture, we are going to describe the resolution and the resolving Rayleigh criteria of resolving power. So, let's begin. First, we will read wave phenomena of resolution. In resolution, the astronomers tell us that many of the stars that we observe with the naked eye are in fact binary star, that is, that we see as a single star actually consists of two stars in orbit about a common center. Furthermore, the astronomers tell us that if we use a good telescope, then we will actually see the true star. We will resolve the single point source into its two concept part. So, what is it that determines whether or not we see the two stars as a single point source? That is, what determines whether or not two sources can be resolved. About our eyes, in each of our eyes there is an aperture, the pupil through which the lights enter. The light is then focused by the eye lens onto the retina, but we have seen that when light passes through an aperture, it is diffracted, and so if you look at a point source, a diffraction pattern will be formed on the retina. If we look at 2 point sources, then diffraction pattern will be formed on the retina, and these patterns will overlap. The width of our pupil and the wavelength of the light emitted by the source will determine the amount that they overlap. But the degree of overlap will also depend on the angular separation of the 2 point sources. We can see this from the next diagram. This is the diagram in which two sources S1 and S2 are represented here. S1 enters when the light from these sources S1 enters the eye and is refracted by the pupil such that the central maxima of the diffraction pattern is formed on the antenna on the retina at P1. Similarly, light from S2 produce a maximum at P2. If the two central maxima are well separated, then there is a fair chance that we will see the two sources as separate sources. If they develop, then we will not be able if they if they overlap, then we will not be able to distinguish one source from other. From the diagram we see, as the sources are moved close to the eye, then the angle theta increase, and so does the separation of the central maxima. Now the Rayleigh criteria. Rayleigh suggested how much they should be separated in order for the two sources to be just resolved. If the central maxima of one diffraction pattern coincide with the first minima of the other diffraction pattern, then the two sources will just be resolved. This is known as the Rayleigh criteria. In figure, this is clearly mentioned. First, this is the figure of well resolved where both the sources are well resolved, just like S1 and S2. This is also the condition of well resolved where sources are represented by S1 and S2. But this is the condition of just resolve. Rayleigh criteria minimum of S2 coincide with maximum peak of S1. This is the condition of not resolved, where both the sources are interfere with each other. In diagram 3, the two sources will just be resolved, since this is when the peak of the central maxima of one diffraction pattern coincide with the first minimum of the other diffraction pattern. This means that the angular separation of the peaks of the two central maxima formed by each source is just the half angular width of one central maxima. From m lambda equal to d sin theta, if m equal to 1, then sin theta is very small or it is equal to theta, and if we put the value of sin theta, then the equation convert in theta equal to lambda upon d, where d is the width of the slit through which the light from the source passes. However, from the diagram of the two sources above, this is just the angle that the two sources subtend at the slit. Hence, we conclude that two sources will be resolved by a slit if the angle that they subtend at the slit is greater than or equal to lambda upon d. We started this discussion on optical resolution with the eye as the slit, but the eye is not a slit but a circular aperture. So, to find the resolving power of the eye, we have to know the half angular width of the central maxima of the diffraction formed by a circular aperture. Tricky calculation, it can be shown that, as we know, lambda equal to a sin theta, where a is the aperture of a rectangular objective. It can also be shown that theta is equal to 1.22 lambda upon b for a circular aperture and a small angle where b is the diameter of the aperture. A circular aperture will resolve two sources if the angle that they subtend at the aperture is greater than or equal to theta equal to 1.22 lambda upon b. As mentioned above, the angle theta is sometimes called the resolving power, but should more accurately be called the minimum angle of resolution. Clearly, the smaller theta, the greater the resolution resolving power. These are the example. If we take the average wavelength of white light to be 500 nanometer, which is in between 400 to 700, the average diameter of the human eye to be 3 mm, then using theta equal to 1.22 lambda upon b, the resolving power of the eye is about 2 into 10 to the power minus 4 radian. So, suppose that you are looking at car headlights on a dark night and the car is a distance capital D away. If the separation of the headlight is say 1.5 meter, then the headlight will subtend an angle 1.5 upon capital D. The this is the routine example of our life. Your eye will resolve the headlight into two separate sources if this angle equals 2 into 10 to the power minus 4 radian, that is 1.5 upon capital T equal to 2 into 10 to the power minus 4. This gives D equal to 7.5 kilometer. In other words, if the car is approaching you on a straight road, then you will be able to distinguish the two headlights as separate sources when the car is 7.5 km away from you. Actually, because of the structure of the retina and optical defects, the resolving power of the average eye is about 3 into 10 to the power minus 4 radian. This means that the car is more likely to be 5 km away before you resolve the headlights. This is the one of the example of resolving power. In case of microscope, resolving power is 1.22 lambda upon capital D, where D is the diameter of the aperture. Significance of resolution in the development of device. In case of CDs, the information on the drive is read by laser reflecting from the sources. A laser with a higher resolution can read more information from the surface of a disk. Significance of resolution in the development of physics, in the development of devices. These are the two more example. In case of electron microscope, electrons are propagated with a very short wavelength through a species. Hence, the image produced is very clear due to the microscope's high resolution power. In case of radio telescope, the wavelength of radio waves is large, so the telescope needs to be large so that the resolution is good. Thank you for watching and listening the video.